Okay. Okay. There we go. All right. This takes it a second to settle in. Then it's usually really fast, but she's just being goofy this morning. I don't care about that cloud recording. All right, here we are. Are we ready now? Sorry. Thank you. Thank you for bearing with me while I dealt with technical difficulties. So we're good now. So we are talking about acids and bases a little more, and then even at the beginning of Unit 8, which we're about to start next week, we're still gonna have a little. There'll be a test after this lesson. There's a test. Your Unit 7 test. So we're gonna be talking about titrations today because we're doing a titration in lab this week, but the one we're doing is kind of like it's like an easy shortcut titration. And then 2 weeks from now, we're doing like a full-on titration with burettes. And you had the burettes out week before last, or last week, the big tall glass tubes, the burettes, you'll be using them again. But this titration today, you're just going to be using a dropper, which isn't as accurate as a burette, but it'll work for today's lab. Today, you're going to be titrating an eggshell. So hopefully after this lesson, you'll have a better idea of what that means since you'll be doing it. So first and foremost, neutralization and titrations. Titrations are about neutralizing things. So let's talk about what that means. What does neutralization mean? What's a neutralization reaction, Annabelle?
The neutralization is when you mix an acid and the right acid and the right base to make it neutral.
Yes, and what do you mean by make it neutral?
Well,
Make it.
Hang on, let her answer. What do you mean by neutral? Do you know?
make it into
How about in terms of pH? What would you mean?
7.
That a girl. Okay, 7. Yeah. All right. So it's when an acid and a base mix, and the acid will donate protons most of the time to the base in what's called a neutralization reaction. The final pH of the solution will depend on whether the excess ions at equilibrium are due to a weak acid or base combination or a strong acid or base combination. Now, she just made an interesting point. She said you're going for 7 neutral. And that's true if you have a strong acid and a strong base and like a weak acid and a weak base. But if you have a strong acid and a weak base, or a weak acid and a strong base, your situation's going to be a little different. If you have a strong acid with a weak base, you're going to need a whole lot of base to get to that 7, right? And it's not always equal parts, even if you have two strong components.
Is there any component besides water that has a pH of 7?
Yeah, there are lots of things that have a pH of 7. There are lots of things that aren't acids or bases that just kind of hang, like a lot of things do, but water is kind of what you're aiming for. We do everything by water, right? We do specific heat, the amount of heat needed to raise a certain amount of water by a certain degree. Like water is just kind of our base for all things. If you need a pencil or a pen or something, grab what you need. You're good. So it will depend, the final pH it's saying will depend on whether the excess ions in equilibrium are due to a weak acid or base strong combination or a strong acid or base combination. So if you have a really strong acid and a really weak base, you may never end up with your neutral. You may not get to your 7, but you still might neutralize a lot of what's going on. You're going to neutralize, meaning if you have a strong acid and a weak base, you'll use up all your base, but there'll still be some acid left, so your pH may still be low. So here's a graphic for it. A neutralization reaction occurs when an acid and a base react together in the correct volumes. When they react, they form what? Water and salt. Sometimes a gas, but water and salt always. Sometimes a gas. And create a neutral pH of 7. That's what you're going for, is 7. So example, if you have sodium hydroxide and hydrochloric acid and you put them together, you get water and sodium chloride. You guys have seen this, right? Because we've done it in lab now like twice. We've used these same components. And you're aiming for sodium chloride. And you can see if you pay attention, if you look closely,
here's your OH, and here's your H, which gives you H2O. And what's left over? Your Na and your Cl, which gives you NaCl. So it's the H plus ions from the acid and the OH negative ions. So it's the hydrogen ions and the hydroxide ions. Remember, OH negative is hydroxide that form the water. And then whatever the other components of the acids are, form your salt. Right on. So this is just a funny note. Neutralization happens in the US while neutralization happens in the US and probably Canada. What am I showing you there?
Different spelling.
It's different spelling. Yeah, we spell it with a Z, don't we?
Neutralization.
Yeah, and they spell it with an S. So if you see it with an S, it's probably coming from the UK, Canada, maybe Australia. If you see it with a Z, it's coming from us, right? That's where it was written. That's all, right? Just sometimes words like that. It's like color. How do they spell color in the UK? Do you know?
COLOUR.
Yeah, they add a U. CLOUR.
Color.
Color. Yes. Right. So it's a thing. All right. So titrations. So what's a titration? Who can tell me what a titration is? Eunice?
Analysis of acids and bases.
Yes. So it's a quantitative analysis. It's an analytical method in which a standard solution is used to determine the concentration of an unknown solution. All right, so what do I mean by that? An acid-base titration is quantitative analysis of acids and bases. Though in this process, an acid or base of known concentration neutralizes an acid or base of unknown concentration. So if you look at this picture here, you see that burette? There it is again, right? I told you they're coming back. This today, you're going to be using a dropper, like a pipette, a dropper. And it's going to act the way that burette is acting here. And then you have your little flask. They're calling it a conical flask. What's the other name for that kind of flask? Starts with an E. Erlenmeyer flask, right? Okay. So what's in here is called your analyte. And it is an unknown concentration. You don't know the concentration of that solution. And your titrant is what you put in your burette. And it is a known concentration. And you know the volume because remember I showed you those tiny beakers last week and said this tiny beaker can fill this huge burette because it's very, very graduated. It's very granular. So your measurements are more exact, right? You can tell exactly how much volume you've added. When you put them together, it's called a titrand. Once you start titrating, it's no longer an analyte. The mixture is a titrand. Okay. So you don't know the concentration of what's in your flask, but you do know the concentration of what's in your burette or dropper. So the titration process can be monitored by visual indicators, pH electrodes, or both. So what do we mean by quantitative? We mean we can find this exact volume added to this exact volume to neutralize, which we can tell by pH electrode or by an indicator. And then we can do some math and it will help us find out the exact concentration of our unknown analyte. So again, it shows you here, your titrant is your known concentration, your analyte is an unknown concentration. In this case, your indicator turns pink. Now, do you remember last week when you added one drop of from your dropper, there would be pink for a second and then it would go away as you swirled it around?
H2SO4.
Yeah, when you added that phenolphthalein would light up for a second and then as you swirled, it would go away again. The absolute best way to do a titration is to put that Erlenmeyer flask on a plate with a magnetic stirrer. So it spins constantly. And then you have to very carefully monitor your titrant and your burette. So your titrant is your substance, such as a reagent solution of precisely known concentration that's added in titration. You know the concentration. You know that concentration, correct. And your standard solution, what's your standard solution? Anybody know? Yeah, so your standard solution is any solution which is precisely known concentration. So your titrant is a standard solution. You know the concentration. So for me, I can know the concentration two ways as your teacher. Are y'all with me? Y'all look like so tired today. So I can order it and it comes in a bottle and I know that wherever it was produced at the factory, I know the exact concentration, or I can make it up myself before you get here and I know the exact concentration because I created the solution, right? All right, so what's an indicator? What you think?
Indicator is what turns the color.
Yeah, so your indicator is a compound that changes color in a solution over a narrow range. Okay, this is important to understand. So look right here. See that? So last week, when we had our phenolphthalein added to our solution, it was clear, right?
Yeah.
And then you added something to it.
Added
What did we add?
NaOH.
Okay, so sodium hydroxide, a base or an acid?
That's a base.
It's a base because it has hydroxide in it. Very good. So as you're adding the base, you're waiting for it to change from acidic to basic. And what most of you saw was you were swirling around and it went from clear to fluorescent pink, like that, like Annabelle's mask, the same color, right? Really bright, really fast, right? But really what happens if you can make your drops very small and very exact, which is what a burette will provide, you get this color, this very light pink. That's what you want. Technically, if it goes that bright screaming pink that we saw, that's called overshot, which means you've added just a little too much of the base and it went too far. There's a range, a pH range where the color changes. So we have things called equivalence point and endpoint. Your equivalence point is the point at which equal amounts of, what's this right here? H3O plus, do we remember? Do you remember, Annabelle?
Hydronium.
Oh, well, she was answering it. Gotta give her a minute. Yes, it's hydronium. Okay, and then what was this one?
Hydroxide.
Hydroxide, right. Okay, so when you have equal amounts of hydronium and hydroxide, that's your equivalence point, okay? And that is determined by your indicator color change and your dramatic change in pH, because suddenly things are usually neutralized right about here. You also have what's called an endpoint. And that's a point during a titration when the indicator shows that the amount of reactant necessary to complete the reaction has been added. And that's when it's like, you know, right at the edge of being overshot, basically. So if you look at it here, you have an equivalence point and an end point. This right here, you see this little area that goes from like 7 to what, 8.5? Yeah. See, or 8.72, it says right here, 8.72. That is your pH range for your indicator. And right here shows for phenolphthalein, this is the range. So anything you're seeing in phenolphthalein is really going from like 8.5 to 8.72. It's really small right there because everything else is overshot. Your litmus paper will do the bottom half here. It'll go from about 8.5 to about 7 within this same range for this particular combination that we're using. And then methyl orange is way down here. So if you're looking for a pH change that is considerably lower, you would want to use methyl orange. But if you're looking for a pH range change that is higher, you would use phenolphthalein. Okay.
So that's what we use phenolphthalein.
Yeah. So the main difference between the equivalence point and the endpoint is that the equivalence point right here is where a chemical reaction comes to an end, while the endpoint is where the color change is like kind of finished. That's the end of the color change. So here's our buddy, Professor Dave. But first, the equivalence point is the point where precisely enough base has been added to neutralize the exact amount of acid in solution. All right, let's see what he has to say. Oh, we're going to get a commercial first. That helps me adjust my volume then.
Whether it's a chef,
Go to Puerto Rico.
or local favorites.
They're going to feed me. I will go.
My grandpa has been in Puerto Rico.
Professor Dave here. Let's
I wanna
talk
go.
about
Sounds good to
titration.
me.
He knows a lot, so it's all with acidity explains. Acid-base titration is a way of determining how much acid or base is present in solution by determining the precise volume of acid or base that will completely react with it. It's like a kind of stoichiometry. On a titration curve for an acidic solution, pH is plotted against the volume of base that is progressively added. As we add base, the pH slowly rises, then sharply rises towards the equivalence point. This is the point where precisely enough base has been added to neutralize the exact amount of acid in solution. When we perform titrations, we recognize the equivalence point by using something called an indicator. This is a substance that will turn a vivid color once the equivalence point has been reached. When we neutralize a strong acid with a strong base, the equivalence point will be 7. If either or both species are weak, this number will vary. For example, let's say there's a solution of sodium hydroxide and we want to know its concentration. Say we react with 3 molar sulfuric acid with 25 milliliters of the base, and we find that it takes 11.6 milliliters of acid to reach the equivalence point. If we convert to liters and then have conversion factors for the concentration of the acid and then the stoichiometric ratio, we can arrive at the concentration of the reactant. Let's check comprehension.
So that's pretty much what we're gonna do in lab today, but instead of using the burette, we're just gonna use a dropper. So it won't be as exact, but it kind of introduces you. So here we are again showing the pH ranges of various indicators. So do you remember last week when, who was blowing bubbles for me? Was it you? It was Lucy. Okay, so what you were using in that case, this bromothymol blue, right? Were you the one that had it turn green? Was it you?
No.
Was it, oh, it was Emerson. Okay, so it turned green to yellow. So look at how acidic you had to make that water, that solution, in order to, that water got more and more acidic because you were blowing carbon dioxide into it and it was producing carbonic acid. You got it all the way down into this range, right? That's fairly acidic with just air. So that was what it took to change it from blue to green. And here's your phenolphthalein again, right? So you get, right here, sorry. But there's lots of indicators. We have methyl violet if you're working with very strong acids and you're just trying to see shifts in here. Thymol blue, this one, look at here. This one changes over a very, very big range. So that would have a different application. Whereas bromothymol blue has a pretty small range. Methyl orange has a very small range. The orange is what you're looking for. And look at how small it is. It's not very far, not much of a pH shift, right? Methyl red, litmus paper. This is bromothymol blue. I'm sorry. You didn't have to go that far. I was reading them wrong. That's bromophenol blue. This is you, Lucy. You only had to get it to about 6, bromothymol blue. So Emerson got blue to about 6, and that's where it came. And then phenol red, phenolphthalein, thymolphthalein, and alizarian yellow. All kinds of indicators. So we have what's called a transition range. So like I was saying, indicators don't change color precisely at one pH value. Instead, over a specific pH range, the color of the indicator continuously changes. The range is different for each indicator. The transition point of an indicator is defined as the point at which the acid and alkaline forms of the indicator exist in equal concentrations. So right here in the middle for your phenolphthalein, this is where you've got equal concentrations, right? So remember that they work over a range. All right, so here's a little bit on indicators, different indicators. This guy looks like he's having a beautiful hike, but no sound. That's weird. Why is there no sound? Please don't be weird. Goodness, it's a long commercial. Okay.
Also ways to determine pH
Why does it
quality.
start in the middle? There we go.
While it is possible to quantitatively measure the pH of a solution using a device known as a pH meter, there are also ways to determine pH qualitatively. In this lesson, we will learn about indicators, which help us indicate the pH of a solution. An indicator changes color depending on the pH of the solution analyzed. Because of this, they are also known as pH indicators. Universal indicator is very versatile as it can measure pH across the entire scale from 0 to 14. It is not a single indicator, but rather a combination of various indicators. If you look at the color changes of a universal indicator according to the pH of a solution, you will find that it resembles a rainbow. If a universal indicator solution turns deep red in a solution, it means that the solution is strongly acidic. with a pH of 1 to 2. If the universal indicator solution turns green, it means that the solution is neutral with a pH of 7. If the universal indicator solution turns dark blue or purple, it means that the solution is strongly alkaline. Universal indicator paper works in exactly the same manner. Litmus is another indicator commonly found absorbed onto paper as litmus paper. Blue litmus paper turns red under acidic conditions, pH less than 7. Red litmus paper turns blue under alkaline conditions, pH greater than 7. Phenolphthalein is an indicator commonly used to determine the endpoint of a strong acid, strong alkali, or weak acid, strong alkali titration. It goes from colorless to fuchsia pink at a pH of 8.2. Methyl orange is used to determine the endpoint of either a strong acid, strong alkali, or strong acid, weak alkali titration. It is red at a pH lower than 3.1 and yellow at a pH higher than 4.4. In conclusion, indicators are substances that change color at a certain pH.
Yep, British.
The point at which an indicator changes color is known as its endpoint, which can be at any pH. Common indicators that you will encounter are universal indicator, litmus in the form of litmus paper, phenolphthalein, and methyl orange.
Don't they spell gray as G-R-E?
Yeah, yeah, EY, yeah, EYAY, that's another one that's weird. Okay, this one is really cool. So I want you to watch closely what happens here. So what he's doing is he has an acid, I believe, in the giant beaker. What's the volume of that beaker, do you suppose? I'm guessing it's about 4 liters or
Liter?
yeah, I'm guessing it's about a 4-liter beaker because the big beaker that you guys pour your waste into over there by the dishwasher rack is a liter. It's 1,000 milliliter beaker, and that looks about 4 times as big. Now, what he's got in this last flask over here, or first flask, however you want to do it, the one on the left, the little guy there, he has some ammonia gas that he's created in a reaction, and ammonia is basic. So you're going to watch a pH change, and this is really pretty. It goes this direction, and then it comes back the other direction. So you can watch, and this is with a universal indicator because it has the rainbow spectrum. So if you watch, this one's just really pretty. Like, it's pretty to watch.
I have 12 students. Mr. Pignara and I.
And the universal
set up
indicators orange like
this
that.
Demonstration
So
for
that's
you,
what's in there.
to give an illustration of indicators, and look at some properties of both ammonia, and its influence on universal indicator. So, Mr. P and I, what we did
Actually, I think he
is,
just has water in here. Yeah,
we
he'll
set
tell you.
up this apparatus, and all of these bulbs are connected to each other through these glass tubes. So it's essentially like one chamber.
You see how he's
but
got gravity
you've got
working, right?
Obviously, these
The
different
angle.
locations of volume. What we did is we flooded the chamber, starting with the, with this over here, with ammonia gas. We produced the ammonia gas through a reaction. And the ammonia gas is, getting, lower and lower in concentration as we move over here, to this final ball. In the big beaker, we have, molarity of 2 molar acetic acid.
Okay, acetic
and
acid,
about
so vinegar.
1,500 mils of water. And we've got a bunch of universal indicator in there as well. So you can see the color that is showing as acidic. So what I'm gonna do now is I'm gonna add a small amount of distilled water up to the top. just that rim in. And I'm gonna open. So right now it's closed, letting in the water. And then I'm gonna close it out quickly.
Watch these colors. Be sure you're watching because they're going to change before your eyes. So you don't want to miss it. Remember, he said the ammonia is more concentrated at that end, less concentrated at this end.
Oh, it's from acidic to base.
Because this is acid in here, right?
So now what I'm gonna
Base
do,
down there.
holding up. pH scale here for the various colors. We need to take note of what color each one of the bulbs is. So you have that red beginning. Pretty green. This one's blue. This one's a deeper purple color. This up here is pretty much the same color as this bulb here. So now what I'm gonna do is I'm gonna open up the valve again. And we'll see what happens.
So he's speeding it up by 4 times. You can watch that drains out. And that's more neutral. So it's pushing it more neutral all the way down, see? More basic. It's pushing the more basic fluid all the way down to the end. You can watch the color change, see it?
Oh, it's down there.
And look at the beaker. Now the beaker's changing color. Isn't that pretty though? It's really pretty what he did.
So what started out as a very low pH at the beginning of the acetic acid, started out with a pH of maybe 0 or 1. Is now up to a pH of approximately 10 or 11 in here. As the ammonia essentially was dissolved, okay, and has created the alkaline environment.
So that's interesting, right? So there's his details right here. He says the ammonia gas, NH3, was created by adding, what's this one?
Sodium hydroxide.
Yes, sodium hydroxide and ammonium chloride is what that is, together and heating it with a Bunsen burner. The acetic acid solution was prepared by diluting 30 milliliters of 2 molar acetic acid in approximately 1.5 liters of, what's the D, do you suppose? It's a deionized or distilled water. So we in class, whoops, in class we use distilled water a lot. Why do we use distilled water, do you think?
And if you add like tap water, it has like those crystals.
Yeah, so what does it mean to be distilled? Does anybody know? What is distillation, do you know?
It's very pure water.
What's the process to distill something, do you know?
You heat it up and then the steam is at the
Yes, so that means distilled water is water that has been boiled. You with me, Annabelle and Lucy? Boiled. It turns to water vapor, it raises up and is cooled, and that is collected, which means it's pure water. There's no ions in it. So if I use tap water, there are ions in it, right? There's fluoride in it. There's usually some chlorine in it. There are ions in the water that you get out of the sink. So when we do our labs, we have to use distilled water because those ions in the tap water will throw our results. Also, if I open the distilled water, okay, and I use some of it, but I don't use the entire gallon, I've now exposed that whole surface to air. Over time, that water becomes slightly more acidic. And when it becomes, because you get those hydronium ions, right? They're going to form on their own. We talked about this. So it gets slightly more acidic. So if we're doing like a titration, I really need to use like a brand new jug of distilled water. So here's something else. when you are doing a titration, like we're doing today and then 2 weeks out, it's gonna tell you stuff like rinse your, it'll say things like, take your dropper or your burette, and you're gonna fill it with your titrant, whatever your known concentration is. And then you're gonna drain it all the way out. And then you're gonna fill it again, and then you're gonna use it. So when you're using a burette, or when you're using a dropper, if you're doing a titration, it's so sensitive that if, say we're setting up burettes, so what we have our known concentration of our acid in there, or whatever, base, whatever we're using to titrate with. You have to rinse it at least 2 to 3 times with distilled water all the way through, which you probably saw me, actually, no, you guys were, yeah, you were sitting over here last week when I started pouring distilled water through all the burettes. First I poured tap water through to rinse it, then I poured distilled water through like 2 times all the burettes. But when you get ready to use it, you have to do that again to make sure it's really clean. And then whatever your titrant is that you're gonna be using, you have to fill the whole burette up with that titrant and run it out. Fill the whole burette with that titrant and run it out, and then fill it for using. So that there's no water left in it, so that it is exactly your known concentration. Same thing with your flask that you'll be using. You have to rinse it with distilled water, you have to put your analyte, your unknown concentration in it, swirl it all around, pour it out, do that a couple times before you fill it. Because you need it to be very, very exact in order for it to give you the results you need. So here's a hold on, Elias. There we go, hold on. That was messing up. So Francois Antoine Henri de Croisiel, I think it's de Croisiel. Yeah, he is credited. Sorry, that sun gets right there, doesn't it? You can move over here if you want. Is credited with inventing titration. And what year do you think? Did you see it earlier? What year was it? 1790. So we've been titrating since the late 1700s. This is not new. And he was the first to assemble a titration apparatus, though not in its current form. Do you remember a couple weeks ago, we had a video, and it was like a silly rap song about a certain historic, who was it? Does anybody remember who it was?
Can I guess?
Yeah, you can guess. It wasn't Lavoisier.
Gay Lussac.
Gay Lussac, very good. Gay Lussac actually invented that burette, but he didn't really he was improving upon this titration apparatus that had been used before. And then we have, so where do you think Francois Antoine Henri de Croisiel, yeah, he's French, right? That's pretty clear. How about somebody named Carl Friedrich Mohr?
He was from
I think he's German, yeah. Is considered the father of modern titration. He redesigned the burette. So Gay-Lussac designed it, he redesigned the burette to make it simpler and more convenient to use. In what year were the first textbook on analytical chemistry using titration?
So I'm guessing Gay-Lussac was somewhere in the 1800s, so I'm guessing 1863.
1863, he guesses. Let's see who gets closest for an extra coin. 1863, what do you think? 1863, 1887, Emerson? 1872, Lucy?
1864.
1860, oh, she's getting close. And what do you think, Everly? $1870. Okay, so let's see who gets closest without going over. Anybody? 1855. Who got closest without going over?
1865.
Hey, extra coin. There you go. All right. And anybody want to guess the name of this book?
Carl Friedrich Mohr's book.
Yeah, Carl Friedrich Mohr's book. It was called Lehrbuch der Chemie Analytischen Titration-Methode. I don't speak German, but I've sung it a couple times, but there you go. So that is the name of his book, but it's the analytical method of it's the chemical, this is right here, this is analytical titration. So that's what he's saying. It's about analytical titration. Okay. One last quick video. This one's fun, and you can do this entirely at your house just for fun.
We do business.
And it is fun to do.
We design and test.
And it costs you very little.
Hey guys, welcome back to my view. Today we are gonna do some cool science experiments using some red cabbage.
Red cabbage. Did you know red cabbage is an indicator?
Feel
Oh, yeah, because the subwoofer's beside you. That's why.
You must have learned in school about acids and bases.
Shift it
Also
through,
called
honey, so you can
alkali.
see.
You know if a solution
shift
is
that way.
acidic or alkaline, people use something known as an indicator.
There
They
you go.
come in paper form known as litmus paper or liquid solution. It changes color differently when it meets an acid or an alkali. They are sold at laboratory supply stores, but today I'm going to show you how you can make your own at home from red cabbage. I know it's purple, but it's still called red cabbage, so deal with it.
I know it's
So you take a
purple,
couple
so
of
deal with
big leaves
it.
from the cabbage and put it in a blender. Then add about 3 glasses of water. Distilled water is preferred at this
About
point,
24
but
ounces.
even tap water will work. At least that is what I'm using. Now blend it together until you end up with some healthy cabbage juice.
You got some hairy arms.
Yeah, it does.
I'm going to drain it first using a pea strainer. This is going to take a while since I have to get rid of all this sludge.
Yeah, speeding it up. This must have taken 30 minutes.
Next, I'll filter it through a piece of cloth to remove any small pieces of cabbage left behind. With this, our universal indicator is now ready. Now we need some solutions to test. The measure of acidity or alkalinity is done in pH value. The pH scale has 14 increments. The lower the number on pH scale, the more acidic the solution is. And the higher the value, the more alkaline the solution is. And 7 is the neutral zone. Here are 7 commonly available solutions which we are going to test. Lemon juice, vinegar, carbonated lemon soda,
It wasn't
water,
quite,
toothpaste and water solution, baking soda and water
if you
solution.
look at it, it
and
wasn't
finally
lined up on its
bleach.
chart right.
Now I'm going to pour my indicator into the glasses to see what happens. The lemon juice, being the most acidic of the lot, changes to a bright red color. The vinegar changes to a pink or a less bright red color. The lemon soda changes to pink shade. The water, being neutral, takes the color of the indicator and becomes purple. The toothpaste and water solution changes to a blue shade, which means now we have stepped over to the alkaline zone. The baking soda and water solution turns a bluish green shade. And finally, the bleach, being the strongest base of the lot, dissolves the purple color completely and retains its own light yellow color.
Because it's bleach.
You can see how the indicator
Filled
has
the color.
changed color in all the different solutions. This is a very fun and easy experiment you can try at home for almost free, and it is also an excellent and safe way to demonstrate the concept of acids and bases to kids.
Mm-hmm.
Now, I was also told at school that acids neutralizes alkali and vice versa. So that means if I mix the solutions at the extreme ends together, they should cancel out each other and I should end up with purple color. So let's try it. When I mix the lemon juice with the bleach, there is no effect on the color. The bleach is a much stronger base than the lemon juice is an acid. It will require a lot more of juice to neutralize the alkali completely and turn the color back purple. Next, when I mix the vinegar and baking soda, there is a sudden release of carbon dioxide gas and the whole solution foams and spills over the glass. It is still not completely neutralized, so it is holding on to the pink color, showing that it is still slightly acidic. Finally, when I mix the lemon soda and toothpaste solution, both being a weak acid and a weak base, neutralize each other completely and we get a perfect purple color, same as the water solution. You can also try it out with other solutions to see what you get, and do let me know how it goes in the comments below. Before I go, I'd like to remind you that the selfie drone giveaway
I don't
is
think the
still
drone
going on,
giveaway
and
is still going on. Yeah. Okay. So a couple notes here at the end. Q4 begins next week, which means you have a test this week. So also the most important thing for you guys, aside from doing that Unit 7 test, is to check for overdue assignments. I'm giving you till 3/10, which is kind of like an extra 6 days, because there are a lot of people who are missing assignments. So
Wait, so there's a break?
no, there's no break. Because we're shifting it, like I'm giving you,
Oh.
we're starting Q4 and I'm giving you a couple extra days to get them completed, okay? So you're gonna be going through and making sure, look at your grade book. If you have something missing, you're gonna wanna get that done, okay? All right, now also, super important, gang, look. Just a reminder, my open enrollment begins this Saturday. This Saturday, which means I'm opening it up to the public and I can no longer save your seat. I can no longer guarantee that you will have a seat after Friday. Yes,
Which, I may or may not.
you're already enrolled. You're good.
Yeah, I'm already enrolled.
You're already enrolled. You're good. Okay. For next year for biology. So if you aren't planning to come back, that's fine. We're gonna miss you. But if you are planning to come back and you don't see your name here, remind mom or dad that you gotta re-enroll by Friday. I can't hold your spot. I can't, because last year I had a waiting list 8 people deep and I expect it again. That being the case, if I hold your spot and then you change your mind last minute, I've lost people that were chomping at the bit to get in. All right, so lastly, dun, 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 dun.
Can I vote?
What you need?
I will not be here. I will be joining public school.
Are you for sure? Okay, the last time I talked to your mom, she said something about putting you in next year. So, all right, well, we'll figure that out then. There's an answer. That was like a couple weeks ago, but maybe she just had to meet him. Okay, all right, there you go. Well, then that answers that question. We will miss you, Lucy. So here you go. Unit 7 test study topics. Where do you find these when you're ready to start studying? Where do you find them? In your resources folder in your Dropbox, right? You go to Dropbox, you see the folder that says resources, you click on it. One says test studies, unit test studies, you click on it. One says unit 7. There it is. Yes, sir. You can turn that in if you're done with it. Yeah. All right. So now we are ready for lab. Let's do lab. Kill this video. Bye-bye, world. Oh, no. Maybe. There we go.